At this exact moment, 49 years after it left Earth behind forever, a machine smaller than a small compact car is sending back a signal so faint that by the time it reaches us, it carries less power than a single snowflake landing on your hand. That signal is completely real. It is happening today, right now, as you listen. And buried deep inside the data it carries home is something that genuinely stopped seasoned scientists cold in their tracks. Not a hoax, not a headline trick, but an actual documented mystery that NASA's own physicists have openly admitted they still cannot fully explain, even now. Stay with me, because to understand why this tiny, ancient spacecraft is still confusing some of the smartest people on the planet, you have to go back nearly 50 years, to the moment it left home, riding on top of a rocket, carrying a golden record, a handful of instruments built with less computing power than the key fob sitting in your pocket right now, and a one-way ticket into the dark, a ticket it has never once tried to turn back on. Its name, simply, is Voyager 1. It launched on September 5th, 1977 from Cape Canaveral, Florida, 16 days after its twin, Voyager 2, even though it would eventually overtake its own sibling and become the most distant human-made object in all of existence. At the time, almost nobody expected this mission to last more than 5 years. The engineers built it to fly past Jupiter and Saturn, snap some photographs, gather some data, and then quietly fade into the background of space history. Instead, Voyager 1 refused to stop. It kept going. It kept working. And nearly 5 decades later, it is still talking to us from a place no human-made object has ever been before, a region so far from the sun that sunlight itself takes over 23 hours to reach it. To picture just how far that is, imagine standing at one end of a football field and trying to whisper to someone standing 16 billion miles away, using a radio signal weaker than a cell phone battery running on its last 1%, and somehow, against every reasonable expectation, that whisper arrives. That is what is happening every single day with Voyager 1. Its transmitter broadcasts using something like 22 watts of power, roughly the same as a refrigerator. Light bulb? And yet that signal crosses a gulf of space so enormous that by the time it reaches the giant dish antennas of NASA's deep space network here on Earth, it has to be picked out from a wall of cosmic noise using some of the most sensitive receiving equipment human engineers have ever built. Let's go back to the beginning, though, because the story of how Voyager 1 got out here is just as astonishing as where it ended up. In the late 1960s, a young engineer named Gary Flandro noticed something remarkable while working at NASA's Jet Propulsion Laboratory. He realized that in the late 1970s, the outer planets, Jupiter, Saturn, Uranus, and Neptune, were going to align in a way that happens only once, every 176 years. This rare alignment meant a spacecraft could use the gravity of each planet to slingshot itself toward the next one, gaining speed with every flyby instead of needing to carry the fuel for the entire journey itself. It was called the Grand Tour, and it was one of those windows in history that, if missed, would not come again until the 22nd century. NASA moved fast. Budget cuts forced them to scale the ambitious 4-planet Grand Tour down into what became the Voyager program, focused primarily on Jupiter and Saturn, with Voyager 2 continuing on afterward to Uranus and Neptune. Voyager 1 was given a specific, focused job. Instead of chasing every planet in the lineup, it was aimed for a close, careful flyby of Saturn's giant moon Titan, a world wrapped in a thick, hazy orange atmosphere that scientists suspected might hint at the kind of chemistry that existed on early Earth. To get that close look at Titan, Voyager 1 had to take a faster, steeper path than its twin, a path that would fling it up and out of the plane where all the planets orbit, permanently ending any chance of further planetary flybys. It was a one-way decision, made deliberately, trading future encounters for one extraordinary look at a moon that still fascinates scientists today. Before it even reached Titan, though, Voyager 1 delivered one of the greatest surprises in the history of planetary science. As it approached Jupiter in March of 1979, its cameras captured something nobody expected to see. On the surface of the moon, Io, a small rocky world about the size of our own moon, scientists spotted a plume rising hundreds of kilometers into space. It was not a mountain. It was not an impact crater catching sunlight. It was an active volcano, caught mid-eruption, the first time in human history that anyone had ever directly observed volcanic activity happening on another world. Before this, scientists largely assumed that a body as small as Io would have gone geologically cold and dead billions of years ago, just like our own moon. Instead, Io turned out to be the most volcanically active object anywhere in the solar system, its surface constantly resurfaced by sulfur and silicate eruptions, driven by the immense gravitational squeezing of Jupiter itself. That single photograph rewrote what scientists thought they knew about small worlds and tidal forces, and it happened because one navigation engineer, studying the image to calibrate the spacecraft's position, happened to notice a strange bump on the edge of the moon that turned out to be a volcanic plume rising into the void. Jupiter itself offered up more discoveries. Voyager 1 found a faint, previously unknown ring system encircling the giant planet, along with 2 new moons, Thebe and Metis, hiding in the glare. It photographed the planet's colossal storm systems in a level of detail nobody had ever seen, and it studied the intense radiation belts surrounding Jupiter, environments so hostile that engineers had wrapped sensitive cables in ordinary kitchen aluminum foil just to add an extra layer of shielding, a strangely humble solution, protecting a spacecraft built to survive one of the most violent radiation environments in the solar system. Then came Saturn. In November of 1980, Voyager 1 swept within about 78,000 miles of the ringed planet, and what it found there kept scientists busy for years afterward. It discovered 5 new moons. It found an entirely new ring, later named the G ring. It revealed the astonishing complexity, hiding inside Saturn's rings, a structure that from Earth looked like a few simple bands, but up close resolved into thousands of thin, braided, gravitationally sculpted ringlets, shaped by tiny shepherd moons, tucked inside gaps in the ring material, their gravity carving lanes through the debris like snowplows on an icy road. And then there was Titan. Titan was the reason Voyager 1 had sacrificed its future flybys. And it did not disappoint. The spacecraft revealed a moon larger than the planet Mercury, wrapped in a nitrogen-rich atmosphere so thick and hazy that Voyager's cameras could not see through it to the surface below. Scientists had hoped for a clear view, but instead they got a tantalizing veil, a world that clearly had weather, clouds, and complex atmospheric chemistry, but one that would keep most of its secrets hidden for another 2 decades until the Cassini and Huygens missions finally pierced that orange fog and found lakes of liquid methane on the surface. In many ways, the questions Voyager 1 raised about Titan in 1980 are questions scientists are still chasing answers to today. With its planetary mission complete, Voyager 1's trajectory carried it up out of the plane of the solar system, climbing higher and higher, farther and farther from the sun, into territory no spacecraft had ever charted. For the next several decades, it simply kept going, its radioisotope thermoelectric generators quietly converting the heat of decaying plutonium into the electricity that kept its instruments alive, its systems slowly, deliberately shut down one by one to conserve power for the journey ahead. In 1990, at the request of astronomer Carl Sagan, mission engineers turned Voyager 1's cameras backward, toward the inner solar system it had left behind, and captured one final photograph before the imaging system was powered down forever to save energy. In that photograph, Earth appears as a single pixel, a pale blue dot suspended in a beam of scattered sunlight, utterly insignificant against the vast darkness surrounding it. Sagan later wrote about that image with words that have become part of scientific culture, describing it as a reminder that everything humanity has ever known, every joy, every war, every civilization, every person who has ever lived, occurred on that single mote of dust hanging in a sunbeam. A pinprick of light lost among countless other pinpricks of light scattered across an image otherwise filled with nothing but empty darkness and a few scattered rays of scattered sunlight bouncing off the camera lens itself. It remains one of the most quietly devastating and beautiful images ever taken, not because of what it shows, but because of what it makes painfully clear about our place in the universe. After that photograph, Voyager 1 went dark, at least in the visual sense. Its cameras were switched off to save power, and it continued on, silent and blind, sensing its surroundings only through instruments built to detect magnetic fields, charged particles, plasma waves, and cosmic rays, the invisible textures of space that no camera could ever capture anyway. And this is where the story stops being about planets and moons, and starts becoming something much stranger. For decades, scientists had a working theory about where the solar system actually ends. The sun does not just emit light, it also blows out a constant stream of charged particles called the solar wind, and that wind inflates a vast bubble around the entire solar system called the heliosphere. Inside that bubble, the sun's influence dominates. Outside it, in the space between the stars, an entirely different environment takes over, filled with material, left behind by ancient supernova explosions and the slow drift of interstellar gas and dust. Scientists expected there to be a fairly clean, sharp boundary between these two zones, and they expected that once Voyager 1 crossed it, all of the solar wind particles it had been detecting for decades would essentially vanish, replaced by the colder, denser plasma of interstellar space. In 2012, that is more or less what happened. Voyager 1's instruments detected a dramatic drop in solar wind particles, and a sudden jump in the density of the surrounding plasma, a change so abrupt that mission scientists spent months double and triple checking the data before they were willing to announce it publicly. In 2013, NASA formally confirmed that Voyager 1 had become the first human-made object in history to leave the heliosphere and enter interstellar space, a boundary called the heliopause. It was a genuine milestone, arguably one of the greatest achievements in the history of space exploration. A machine built in the 1970s, successfully carrying a piece of human engineering completely outside the protective bubble of our own star for the first time ever. But here is where the real mystery begins. The one that genuinely puzzled the scientists working on this mission. The one that is not clickbait, but documented, published, peer-reviewed confusion. According to the models scientists had built when Voyager 1 crossed into interstellar space, the direction of the magnetic field around it should have changed noticeably. Inside the heliosphere, the magnetic field lines are shaped by the sun's rotation and follow a particular spiral pattern. Outside it, in true interstellar space, the magnetic field should be oriented differently, shaped by entirely separate forces operating across the wider galaxy. Instead, when Voyager 1's magnetometer measured the field just after crossing the heliopause, the direction barely changed at all. The particle counts changed dramatically, exactly as predicted for entering interstellar space, but the magnetic field pointed in almost the same direction it had inside the bubble. It was as if two completely different environments were somehow lining up their magnetic compass needles in nearly the same way, something the existing models did not predict and, honestly, still do not fully explain. Scientists have proposed a few possible explanations. One idea is that the heliosphere's magnetic field and the interstellar magnetic field happen to be roughly aligned in this particular direction of space, purely by cosmic coincidence, meaning Voyager 1 just happened to cross into a region where the two fields look similar even though they come from entirely different sources. Another idea is that the boundary itself is far messier and more turbulent than the clean, sharp-lined scientists originally imagined, with the sun's magnetic influence bleeding gradually into interstellar space rather than stopping abruptly, blurring the transition Voyager 1 was trying to measure. But neither explanation has been proven conclusively. To this day, the exact reason why the magnetic field barely shifted as Voyager 1 crossed into the space between the stars remains an open, actively studied question in heliophysics, one of the genuine unresolved puzzles left behind by this incredible spacecraft. There is more. In 2013, Voyager 1's plasma wave instrument picked up something scientists did not expect at all, a series of unusual oscillations, essentially a kind of vibration or hum in the surrounding plasma, caused by shock waves rippling outward from solar eruptions that had occurred back near the sun months earlier. By studying how those oscillations moved through interstellar plasma, scientists were able to calculate the density of the material out there directly, and what they found was strange. The plasma outside the heliosphere turned out to be roughly 40 times denser than the plasma inside it, a jump that, while broadly expected in direction, was sharper and more dramatic than most models had predicted. It confirmed that Voyager 1 truly had crossed into a fundamentally different environment, but it also revealed that our understanding of exactly how that transition happens, how gradual or sudden it really is, how turbulent the boundary layer truly is, remains incomplete. Then in 2020, and again through 2022, Voyager scientists reported something else that raised eyebrows. The density of plasma surrounding the spacecraft, now traveling ever deeper into interstellar space, kept increasing, more than scientists had expected based on earlier models of how interstellar material should be distributed. Some researchers have speculated this could mean the heliosphere's outer boundary is not a smooth, simple shape like a comet's tail, but something far more wrinkled, compressed, and irregular, shaped by forces and interactions that are still being worked out using the very same data Voyager 1 continues to send home decades after its instruments were designed and built. And then there was the scare in 2023, the moment many people, understandably, feared might be the end. In November of that year, Voyager 1 suddenly began transmitting nothing but gibberish, a repeating pattern of ones and zeros that carried no usable scientific information at all. For months, the spacecraft appeared to still be receiving commands. Its radio signal was still arriving on schedule, but the data itself made no sense, as if the world's most distant machine had suddenly forgotten how to speak. Engineers back on Earth spent months investigating, sending careful, painstaking commands across a gap so wide that every single message took over 22 hours just to arrive, and then another 22 hours for any response to come back, meaning each attempted fix took nearly 2 full days to test. Eventually, they traced the problem to a single corrupted chip inside one of the spacecraft's 3 onboard computers, a memory chip that had likely been damaged by decades of exposure to cosmic radiation. With no way to physically repair the chip from 16 billion miles away, the team did something remarkable. They rewrote the affected code and relocated it to a different working section of memory, essentially performing a kind of software surgery on a computer running technology from the 1970s, using nothing but patience, radio waves, and extraordinary engineering skill. By the spring of 2024, Voyager 1 was talking clearly again, its data streams restored, its instruments once more reporting back from the edge of known space. Think about the sheer scale of what that repair actually required. Somewhere in Pasadena, California, a team of engineers, many of whom were not even born when Voyager 1 launched, had to study decades-old schematics, some of them printed on paper, some of them stored in formats so old that finding someone who still remembered how to read them was its own small challenge. They had to think like the original 1970s. Engineers who built the spacecraft, understanding a system with a tiny fraction of the memory found in a modern calculator, and they had to do it all while accepting that every single guess, every single test, every single line of new code would take nearly 2 full days to confirm. There was no room for a quick trial and error approach. There was no undo button. Every command sent across that gulf of space had to be right, or very close to right, the first time, because a mistake could mean losing the spacecraft entirely, ending nearly 50 years of continuous operation in an instant. And yet, they did it. They found the broken piece of memory, they moved the necessary code to a working section of the system, and they brought humanity's most distant machine back from the edge of permanent silence. That fix bought the mission more time, but it did not solve the deeper, unavoidable problem facing Voyager 1, which is simply this. It is running out of power, slowly, steadily, and there is nothing anyone can do to stop it. The spacecraft is powered by radioisotope thermoelectric generators, devices that convert the heat produced by the natural radioactive decay of plutonium into electricity. Unlike solar panels, these generators do not depend on sunlight, which is fortunate because at this distance, sunlight T is roughly 900 times fainter than it is here on Earth, far too weak to power anything useful. But radioactive decay follows an unavoidable, fixed schedule. And every single year, Voyager 1's generators produce a little less electricity than the year before, currently losing around 4 watts of available power annually. To compensate, the Monsieur AIM team has had to make increasingly difficult choices, shutting down one instrument after another, powering off heaters that once protected sensitive equipment from the extreme cold of deep space, and carefully rationing every remaining watt to keep the spacecraft's most essential systems alive for as long as possible. As of the most recent reporting, only 2 scientific instruments remain active on Voyager 1. The magnetometer, which continues to measure the magnetic field puzzle that still has not been fully solved, and the plasma wave subsystem, which continues to listen to the electric hum of interstellar space itself. One by one, the other instruments that once photographed volcanoes on Io and mapped the rings of Saturn have gone silent, not because they broke, but because there simply is not enough power left to run them. Engineers estimate that Voyager 1 may be able to keep at least one instrument functioning until sometime around 2036, nearly 60 years after its launch, an almost unbelievable lifespan for a spacecraft that was only ever expected to survive a 5-year mission to Jupiter and Saturn. None of this would even be possible without the enormous dish antennas of NASA's Deep Space Network, a system of giant radio telescopes positioned in California, Spain, and Australia, spaced roughly 1/3 of the way around the planet from one another, so that as the Earth rotates, at least one of them is always pointed toward Voyager 1, ready to catch its signal the instant it arrives. These dishes are staggering feats of engineering in their own right, some of them 70 meters. Across, wide enough to cover most of a football field, built specifically to detect signals so weak that ordinary radio equipment would never notice them at all. Every single day, teams of engineers coordinate the precise timing needed to keep these enormous structures aligned with a spacecraft that is not just far away, but constantly moving farther away, meaning the pointing. Calculations have to be updated continuously just to keep the connection alive. It is easy to imagine Voyager 1 as some lone, self-sufficient explorer drifting silently through space, but the truth is that its survival has always depended on this enormous, patient, coordinated effort back home, an effort that has now continued, uninterrupted, for very nearly half a century. Even after its last instrument finally goes silent, Voyager 1 will not stop moving. It will continue traveling outward at roughly 38,000 miles per hour, carrying with it the golden record bolted to its side, a phonograph disc containing greetings in 55 languages, samples of music from cultures around the world, natural sounds of Earth like thunder and birdsong and human laughter, and a series of encoded images depicting our planet, our biology, and our civilization. It was assembled under the guidance of Carl Sagan and his colleagues as a kind of message in a bottle, cast into the ocean of the galaxy on the extraordinarily unlikely chance that someone, someday, somewhere, might find it and understand what it means. The team that built the golden record spent months debating exactly what should represent an entire species and an entire planet on a single disk small enough to fit in your hands. They chose sounds that felt fundamental to being alive on Earth: the rumble of thunder, the patter of rain, the call of a whale moving through dark water, the cry of a newborn baby, footsteps, laughter, a kiss. They chose music that spanned continents and centuries, from Bach and Beethoven to Chuck Berry, from traditional songs recorded in the mountains of Peru to chants recorded in the forests of Africa. An attempt, however imperfect, to capture something true about human creativity in a form that might outlast every one of us. I included a diagram showing the location of Earth relative to a set of well-known pulsars, a kind of cosmic address written in a language of timing and frequency that any sufficiently advanced civilization anywhere in the galaxy might be able to decode. And engraved on the record's cover is a simple set of instructions, illustrated symbols explaining exactly how to play it, on the almost impossibly distant chance that some future intelligence, utterly unfamiliar with human technology, might one day find this small golden disk drifting through the void and wonder what it was. There's no realistic expectation that the golden record will ever actually be found. Space, even within our own galaxy, is almost incomprehensibly empty, and the odds of Voyager 1 ever passing close enough to another star system for any hypothetical observer to notice it are so small that they barely register as a probability at all. And yet the record was built anyway, polished anyway, bolted to the spacecraft anyway, because the people who made it understood something important, that the value of reaching outward is not only measured by the odds of being received. Sometimes it is simply about the act of trying, about a species choosing, deliberately and thoughtfully, to leave behind the best version of itself, cast outward into the dark, regardless of whether anyone will ever be there to receive it. According to current calculations, Voyager 1 is heading in the general direction of a star system roughly 17 light years away, and in about 40,000 years it will pass within a couple of light years of a faint red dwarf star called Gliese 445. It will not stop there. It will not stop anywhere. Barring an almost inconceivable collision in the vast emptiness of interstellar space, Voyager 1 will simply keep drifting silently for millions upon millions of years, long after every trace of human civilization that built it has changed beyond recognition, long after the sun itself has grown old, long after Earth as we know it has ceased to exist in its current form. Think about what that actually means for a moment. Right now, today, while you are listening to this, a machine built by engineers who assumed it would fail after 5 years is still transmitting data from a region of space that did not even have a confirmed boundary until this spacecraft found it. It is still sending back magnetic field readings that scientists cannot fully explain. It is still humming with plasma wave data from a region of the galaxy. No human being has ever visited or ever will visit in person. Its computers run on less processing power than a modern digital watch. Its data trickles home at a rate slower than dial-up internet from the 1990s. And yet it remains, right now, the single most distant functioning representative of human curiosity, a technological artifact so far from home that light itself, the fastest thing in the entire universe, needs more than a full day to make the round trip. There is something almost unbearably poetic about the fact that the deepest, strangest mystery currently coming from Voyager 1, this unexplained alignment of magnetic fields at the true edge of the solar system, cannot be solved with more powerful telescopes, cannot be solved with better computer models alone, and can only truly be solved by the actual physical presence of an instrument out there in that exact spot. An instrument that happens to be a 50-year-old spacecraft, slowly, deliberately going quiet, 1 watt at a time, its scientific voice fading like a candle burning down to its very last inch, still stubbornly, defiantly lit. Someday, likely sometime in the mid-2030s, Voyager 1 will send its final scientific transmission. Engineers will pick up that last signal, confirm there is nothing left to measure, and mark the moment as the true end of the Voyager mission's scientific era, nearly 60 years after 2 nearly identical spacecraft left Earth on a rare planetary alignment that will not happen again until the year 2153. There will be no dramatic explosion, no final crash, no visible ending of any kind. There will simply be silence where there used to be a signal, a quiet so complete that it will take a while for anyone watching from Earth to be entirely sure that it has actually happened, since even the confirmation of silence will take more than a day to travel across the gap between here and there. Consider, too, everything that has happened on Earth during the years Voyager 1 has been quietly traveling away from us. When it launched, there was no internet as we know it, no personal computers in most homes, no cell phones, no idea that the Cold War would eventually end, no idea of the countless changes, technological, political, and cultural, that would reshape human civilization over the following decades. Entire generations have been born, grown up, and grown old in the time Voyager 1 has spent traveling outward. Wars have started and ended, empires of technology have risen and been replaced by newer ones, and through all of it, this one small spacecraft has continued its steady, uninterrupted march away from everything familiar, utterly indifferent to the noise and change happening back on the world that built it, carrying instead a single, quiet, unbroken purpose to keep measuring, keep listening, keep sending home whatever small fragments of understanding it can gather from a part of the universe no one has ever reached before. And after that silence falls, Voyager 1 will not stop existing. It will simply stop talking. It will continue on its long, lonely, uninterrupted journey outward, a cold metal shape drifting through the dark, carrying humanity's golden record and the ghost of every discovery it ever made, from the volcanoes of Io to the mysterious, unexplained magnetic boundary at the true edge of our solar system, a boundary it found first, and a mystery it may end up taking with it, unsolved, into the endless night between the stars. That is the real story of Voyager 1, not a spacecraft that turned around, not a discovery too shocking for scientists to explain, but something far more quietly astonishing, a 50-year-old machine running on fading plutonium and 1970s-era circuitry, still pushing the absolute frontier of what humanity knows about the universe we live in, one faint radio whisper at a time, carrying real, documented, still unresolved questions about the true nature of the boundary between our solar system and the galaxy beyond. And perhaps that is the part of this story worth sitting with the longest. Not the volcanoes on Io, not the golden record, not even the strange, still unexplained magnetic field at the true edge of the solar system, but the simple, almost stubborn persistence of the thing itself. A machine built by people working with slide rules and punch cards, never designed to last this long, never expected to still matter this much, and yet here it is, still functioning, still useful, still teaching us something new about the universe nearly half a century after anyone thought it would go quiet. Somewhere out there right now, 16 billion miles from where you are sitting, older than most technology you will ever own, it is still moving, still listening, still speaking into the dark,